Hello, my name is Benny Schundelmier. I study physics at the University of West Florida. I've had the pleasure of working with Dr. Laszlo Uwe studying spectroscopy at the Laser Lab in the Hall Marcus College for Science and Engineering building. Today we will be presenting a poster of our results that were recently published in the Journal for Vibrational Spectroscopy.
Hey, I am Dr. László Új, Professor of Physics at UWF. The poster and this presentation is the summary of the experimental and theoretical background of two-beam three-color coherent Raman spectroscopy. We have applied the method to measure low-frequency molecular vibrational spectra. The scientific results published in 2 research articles very recently. First, we are going to present the experimental and laser spectroscopy system. The brief discussion of the light-matter interaction follows. The measured polarization sensitive spectra of 2 well-known, very important chemicals will be explained. Get ready for the brainstorming.
Displayed is the poster summarizing our research on the three-color two-beam broadband method. The 4-wave mixing process allows for non-resonant signal suppression relative to the polarized and depolarized Raman bands. We use this method to measure low-frequency polarization-sensitive vibrational spectra of chloroform and carbon tetrachloride. We want to express the validity of our system, as this method is not fully recognized for ultrafast Raman spectroscopy. Please feel free to pause the presentation and read the poster in its entirety. Through the next few slides, we will be highlighting the major points of our research. This is a sneak peek into the laser lab at UWF with a schematic of the Coherent Raman Spectroscopy tabletop setup. The major light source is an injection-seated nanosecond neodymium YAG laser coupled with a broadband optical parametric oscillator. Adjustable beam expanders and limiting apertures were placed into the beam to flatten wavefronts and ensure maximum spatial overlap after focusing the beam into the sample. A Glan-Thompson polarizer was used to select electric field components of the signal to be measured. A 600 nanometer low-pass filter was placed in the OPO beam to eliminate the signal from the two-beam coherent anti-Stokes Raman scattering. An imaging spectrograph with coupled fiber optics was used to record the spectra.
In this slide, we represent the 4-wave mixing process responsible for two-beam three-color coherent Raman scattering. Figure 2 shows the material-photon interactions of the multi-photon process on the energy level diagram of the sample molecule. 2 photons with frequencies omega b and omega b prime, creating oscillating vibrational coherences. These photons are coming from the broadband radiation. The probe photon with the frequency omega naught couples to the signal photon emission to the evolving coherence. The inset on the figure is the spectrum of a measured signal. Figure 3 shows the measured low spectral resolution spectra of all the contributing radiations. The large broadband spectrum on the left is the spectrum of the optical parametric oscillator. It is well separated from the signal. The two-beam three-color broadband signal is centered at high 32 nanometer at the wavelength of the narrowband radiation.
Figure 5 and Figure 6 show the polarization-sensitive spectra of carbon tetrachloride and chloroform, respectively. Each spectra shows that at determined polarization angles of the analyzer, specific vibrational modes are suppressed. These results support the theoretical understanding of polarization-sensitive CARS spectroscopy. Coherent vibrational spectra of 2 well-characterized samples were measured to demonstrate the practicality of the method. Significant signal suppression of the non-resonant background together with spectral window selection can increase the contrast in the coherent Raman microscope. In order to make the measurements more robust, the fiber optics-based detection system and multi-pass broadband spectral filtering stage were developed. Currently, we are using this technique to record polarization-sensitive vibrational spectra of crystalline samples. We are confident this method can be expanded with the use of ultra-fast laser pulses. If you would like any further information on our research, please read our 2 publications. That is a wrap, you guys. Thank you for joining us today. I wanted to say a special thanks to the Office of Undergraduate Research for their travel award program. I've been able to travel the country presenting research at multiple national conferences. Thank you, Dr. Laszlo Uwe. It's been a pleasure working with you, and a special thanks to the Department of Physics. If you guys have any questions, concerns, comments regarding the presentation, don't hesitate to email either Dr. Uwe or myself. Thank you for joining, and I hope you have a good day.